Good evening, everyone. I welcome you to the webinar on water sufficiency for your building and occupants today. I am Yashima Jain and I'll be moderating today's session for you. Next slide, please.
Just a minute.
Yep. First, I would like to acknowledge the support of the Department of Science and Technology and the Ministry of New and Renewable Energy. I would also like to acknowledge the support of the sponsors and affiliates for Solar Decathlon India. Next slide. Now today we are happy to announce the top learners so far. These 4 students have completed all the self-learning modules. Let's see if they become our quiz winners too. Now remember, the quiz will be available on November 11, 10, 11 and 12, and the questions will be largely based on the learning materials from the first 5 learning modules. Next slide, please. So today's webinar is being conducted by Sanjay Prakash, one of the foremost practitioners of sustainability in building and community design. Sanjay Prakash is an architect with a commitment to energy-conscious architecture, eco-friendly design, people's participation in planning, and production design. His area of practice and research over the past 30 years includes passive and low-energy architecture and planning, hybrid air conditioning, autonomous energy and water systems, bamboo and earth construction, community-based design of common property, and computer-aided design. Under his guidance, hundreds of individuals have developed capabilities in performing design, conceptual or management work in these areas. Sanjay is also a group of advisor for Solar Decathlon India. Sanjay, we look forward to your presentation today.
Thank you.
Also, today Sanjay will discuss the process of water cycle design to reach water sufficiency, case studies of building and community scale projects with water sufficiency goals, various technologies and its impact on construction cost and maintenance. Now, as always, you are free to send in your questions in the chat window or the Q&A window. We will take as many questions as time allows during the session. And with that, it's over to you, Sanjay.
Thank you. So I wanted to begin my talk by explaining something that has been there in the self-learning module also, that we can't live without water. We can surely live without energy, without external sources of energy, but we can't live without water. It's very essential for human life. And I thought this picture, which shows the river with the 2 Roman aqueducts going across it, is an excellent way to remind ourselves that many civilizations, human civilizations, were built around sources of water, be they rivers such as the Indus Valley civilization in India, or be they water that was got in for the large populations from aqueducts. So that is the importance of water. Although freshwater resources on Earth, they seem quite large, but they are quite limited, and therefore it acts as a limit to the human population as a whole. For example, you see in this left-hand pie chart that even though there's a lot of water on the Earth, the freshwater component of that is only 2.5%. And further, if you blow up the 2.5% freshwater, you'll find that, say, applying WHO standards, most of it is unsafe. I'm sorry, I lost that. 0.07%. This is wrong. This unsafe 2.5% is not true. It's 99.93% is unsafe, and 0.007, I'm so sorry, percent is safe for drinking. So it's a very minuscule amount that is good for drinking. But then drinking is not the only thing we do, of course, when we talk about water. The other property of water, which is unlike energy, is, well, or like energy, is that it changes form, but is not created nor destroyed. So it can change state, such as this ice glass that you see here, and that's frozen, and it's there in the water vapor as well. And it can change its quality, its degree of purity as well. So, for example, you can have this wastewater also, and you can have a pristine pond also. So you can have all kinds of water that are available, and most of it remains pretty much constant in the Earth's crust. And it's not really created nor destroyed. It just changes form. It changes purity. It changes state. So this is the important thing about water. And see, these are the global freshwater resources available. This is similar to the earlier graph. So you see that so much water, 96.5% water is contained in the oceans, which is all saline because it contains washed off salts to create 3000 ppm of impurity. Then amongst the land, water on land, there is saline water in various forms. That is a small amount, 0.9%, and there's fresh water, 2.5%. So it's this fresh water we are interested in, right? Now, if you blow up the fresh water, you see that there is most of it is locked in glaciers and ice caps, some nearly 70%, and some 30% is there in groundwater. So actually what we see as surface and other fresh water, that is to say rivers and lakes, is just 1.2% of that 2.5% which is fresh water on the earth. And then if you blow up that 1.2 also, you find that the bulk of it is in ground ice and permafrost. So it's not actually there available. Ground ice is not being counted in groundwater, but can be also. So that's a question of definition. Now, lakes occupy the bulk of the fresh water that is available to humankind. And of course, there is in the soil moisture, there is some water, there is some water in water vapor in the atmosphere itself, and so on. So there is a lot of water in all kinds of stuff, including living things. But you see, rivers, which we consider as the primary source of water, just occupy 0.5% of 1.2% of 2.5% of the total endowment of water available to us. So it's really a very small amount, and it seriously limits the human population to possibly something not very much more than 10 billion people, and we are reaching that soon. Water has a geostrategic importance as well, or a geopolitical importance. So, for example, one of the largest rivers in Asia, the Brahmaputra and the Indus, they start from pretty much the same area in China, and they cross over into India in the area of Spiti. And in a sense, you could say that China holds the tap to India, and India in turn holds the tap to Indus, which feeds Pakistan mainly nowadays. And yet, this is not to say that the tap can be turned off easily, because a variety of treaties, including the Indus Valley Treaty, Indus Waters Treaty, signed in 1947, have ensured that we can't really turn the tap off on Pakistan in terms of Indus. Also, it's impractical to turn taps off, right? I mean, what would turning taps off mean? It would mean creating a huge lake on our side and being able to create sufficiently large size of lakes so that all the water of the Indus continues to always be stored on this side of the border. And that's not practical, neither for China nor for India. So we actually don't do it. And we have, even during the wars that we have been engaged in with Pakistan, we have not really ever tried to shut off the tap, as it were. The treaty basically says that all tributaries of the Indus can be dammed, but not the Indus itself, because that right has been given to Pakistan. So here we are. Now, water use in India, I think you need to understand, is mostly for food. This is 78% goes into irrigation. And so when we talk about water conservation, we talk about turning the tap off, or taking shorter showers and stuff like that, or bathing in a bucket and so on. But if you see, the easiest way, and this is true of me also, the easiest way to actually reduce a lot of fresh water use in India would be to turn vegetarian. Why vegetarian? Because, say, pulses and grain take up 300, 400, 500, 600 liters of water for every kilogram of food, while, say, red meat of any kind, not even beef, but mutton, takes up 20,000 liters to create 1 kilogram of meat. So, indirectly, of course, it goes into the making of the pastures, into the growing of the grass, and to feed the animals and so on. So you see how most of the water that we use is in irrigation. And for those of you who know this country well, you also realize that politically, this water and even the electricity that pumps up this water in the farms has been traditionally given free. And therefore, it's been so bad that farmers have even left their not installed switches on their pumps, so that when the electricity comes, the pump works and groundwater is pumped in on the field. So one theory is that it goes back to the ground, which means that we are recycling the water. That's simply not true, because much of it is evapotranspired into the atmosphere, and quite a substantial portion goes into making the food itself. So that is where the bulk of the water goes. Domestic use is only 6%. In fact, industry is only just behind that. And the power sector, which can be clubbed with industry if you want, and then therefore make industry 8%, the power sector uses water for cooling. So a very large amount of water mostly evaporates in the power sector, whether it's nuclear power plants or thermal power plants or whatever, because when crucibles need to be cooled, then you require water to be evaporated and cause that cooling, which is how this is used. So, and other sectors of the economy use 8%. So there are various uses for water. So you see how domestic water, which we consider as the most important thing because we can influence it as architects and engineers, is not as important as food choices are. And we actually don't understand how climate change will affect all this availability. We are saying that, okay, we have a limit of 10 billion people on this earth. Will climate change cause rain to fall more often? Answer by most scientists is yes, more intensely, and therefore water will run off and not collect. The answer seems to again be yes. Will there be greater number of droughts? The answer is again yes. So how do we reconcile these difficulties is something that I would rather leave to you to find out, because the answers are complex and contradictory. And it's not easy to say how climate change will affect all this availability of water, except to generally say that generally it's assumed that water scarcity will only tend to increase rather than decrease. I have used the term groundwater. I would like to change the term now to say it's fossil water. Why is it fossil water? Because like fossil energy, coal and oil, it is stored in the ground for over long periods of time. And when we draw it using pumps, then we don't necessarily take our endowment of this year's water or this season's water. The only renewable water really is rain or snow, of course, all kinds of precipitation. And therefore, if we really want to be strict about net zero water, then we should be talking about only renewable water and not really fossil water. Now, let's come to the use side. What is the standard of use that we are supposed to be using in our domestic use. Now, remember, the grand total amount of fresh water used in India translates to 1600 liters per person per day. Of that, only 135 liters is used domestically, or should be. Often, this 135 liters is not available. Therefore, most countries, especially most cities, especially in the north, get less than this. So now you see 135 liters, 30-40% gets into leaks. Of the remaining part, another 6 to 8% goes into post distribution leaks. So the actual usage in urban areas is 75 to 115 liters, and this is how it's distributed. 29% drinking and so on and so forth. You can just read the whole chart. And you see how this doesn't all require the same quality. So clearly drinking requires, let's say, WHO standard water, but laundry doesn't necessarily require the same degree. Washing utensils similarly may not require the same degree. And I've also discovered that some water engineers have done something quite interesting. They wash with dirtier water and they do a final rinse with clean water. So that's another way of fooling this quality parameter and getting there. Now, these are the various classes of water that are classified by CPCB, the Central Pollution Control Board, where class A is drinking water, class B is outdoor bathing, which in an organized way, class C is drinking water source after conventional treatment and disinfection. Class D is propagation of wildlife and fisheries, which is different. And class E is irrigation, industrial cooling, controlled waste disposal, etc. So in fact, class E can often just be treated sewage water because each of these classes, as you can see, creates a waste stream. So we tend to use class A water in our domestic supply pipelines in our cities. And that, to my mind, is a problem because it means that we are using the same quality of water that is drinkable as well as for flushing, which seems to me like a class C or a class D usage. But anyway, this is the tradition because this tradition has been handed down to us, I think, from Western societies which developed cities in the 20th century. And we must remember that most Western societies are highly water positive. In the Netherlands, for example, or in the US, you have the water supply issues have been generally sorted out in the early part of the 20th century or even in the late part of the 19th century, with projects like Tennessee Valley Authority and so on being big time suppliers of water. And they generally don't consider water as a big issue. And this is one reason why in India also we haven't considered water as such a big issue, probably because we ape the West. Unfortunately, it's today become a political hotbed because you can't even start costing water for what its worth is in true fact without creating a political upheaval, because people consider water a free gift of nature and would rather, even farmers who use most of the water would completely rebel if water was priced. Let's come now to net zero water design. Now, net zero simply means that you either use renewable water, what is available to you, or you recharge that fossil water that you draw, if you draw some, the same quantity. So this is the principle of net zero. And here are the steps to achieve it. The step first is you have to find out what is the available non-fossil water and see how best you can use it. So this was a graph of 12 months of water availability depending on rain. We are mostly in monsoon climate, so you will see that June, July, August, September we have large quantities, and then most other months we have small quantities. But our usage is pretty much constant throughout the year, which stands to reason, right? So this is the total amount of water available. because we don't irrigate in the monsoon months, our actual consumption goes down quite a bit. Then the second step is to reduce the amount of water we use, at least domestically, not just with vegetarianism, which is, of course, one possibility which you can't really assume in your decathlon project. You'll have to assume some kind of a food habit which is average, whatever that means. So, but you can reduce it with efficient fixtures. So, for example, I had done this study, which you see in these 6 pictures, some 15 years ago, when I was to build a house, in order to find out what is the real consumption of various faucets and shower heads, in this case, shower heads. So you see this shower head, 1, 2, 3, 4 are the same shower head. And this is one of the settings of that shower head, which just gives a mist like spray. And this is the heavy setting, which gives, by the way, this same picture is of this same mist, but taken with a flash. So you can see the droplets now. While this is the full setting, where this is without a flash, this is with a flash. So you see how the colors change and how the accuracy of the droplet showing changes. And the same thing is happening here. So no, this is not the same thing. This is taken in the same light. But this was something that I bought called the lowest flow shower head ever. And this was available on kind of mail order catalog. So it was available in the USA. So I got it and I fitted it and tested it out. Very interesting is that even at very high pressures, which is what I was testing it with, the maximum it delivered was 2.8 liters per minute. And it was quite satisfactory to shower in that. And when, even with your eyes closed, you push this little button, I'm assuming that my cursor can be seen, my arrow can be seen. When you push this little button in, then this water reduced to a dribble so that you can still do soaping, and it's about whatever 200 grams per minute or something like that, 200 milliliters per minute. So you get much less for those few minutes that you're doing some soaping. So you can actually reduce even from 2.8 liters for a while. And I found that with using this, we could not use more than 10, 15, 20 liters in a shower, while the normal usage pattern is 30, 40 liters for a typical person. So here is my analysis and bar charts of what I found. And I did this very simply by using a stopwatch and Bisleri bottle of 1 liter to find out how many seconds it took to fill 1 liter. And these 2 bars that you see in groups are with aerator. No, this is with the partial opening, this is full opening. So you see every faucet has 2 settings. So this was how it was. So now the soaping setting is 400 GPM. Not, I was wrong, not 200, but 400 GPM. And so this is that set of thoughts that you can read at your leisure. I think these will be available to you in the form of videos.
Yes, there will be, the recording of the webinar will be available.
Yeah, so in that case, I suggest that you people have a look at the thoughts that came up while this bar chart was being made. So this was set low, set full, and I discovered that, which is not in this graph, here it is. In the bath area that I had in the apartments, I discovered that there's a horrible 38 or 37 liters of water that flowed in every minute when I set it to full. Though, of course, when it was set to less than full, it was as less as 7 liters per minute. But that was the kind of water that flowed. So that means in 1 minute, you could end up using your entire day's endowment of water. And later on, I figured that the reason for this was that this was a master bedroom, and the designer must have thought that people will fit a tub in it And of course, tubs don't get easily filled up because they're 200-300 liters. And you don't want to wait more than 10 minutes. You don't want to wait more than 10 minutes to fill it up. So something like 37 liters per minute is what is required to fill a tub properly. So that made me realize that I should not desire a tub in my new house, and I did not have one. And we used low flow showers only. And this was the result of the other shower settings that you can have a look. The third step then, having established some kind of a reduced use of the renewable water, the third step is to reuse that water within the network. This is a diagram from a project that we did in Bangalore. And this shows that there is rain and it comes to three places. One is the soft roofs, the roof gardens. Four places, sorry. One is the hard roof where it flows off and gets collected into rain-fed tank. The third part goes to the sky garden, which was a special feature that we had in that particular project. And then the open landscape area it falls on. So this goes to the recharge pits and finally to the ground. So everything later on is stored in the shallow aquifer and can be pumped back up into an underground tank, and from there it was treated and so on. So you will see, if you spend enough time on this diagram, that broadly rainwater was used in this project to provide most of the water, sometimes from the ground, but mostly from straight away from stored rainfall harvested water, which was a very large tank. I remember something like 4 lakh liters were stored for 100 houses. No, 40 lakh liters, 400 cubic meters, yeah. So that was a lot of storage. And no, it was 4,000 cubic meters, sorry. So that was a lot of storage. And then the water went in various ways to various places. For example, the white water, as I call it, or the blue water, as your notes call it, which was the good for drinking water, can go and start feeding people. Following that, you had a demand for hot water in some places. So just like you have the need to have the hot water went into the fridge only because it was also a hot and cold water dispenser. It was a customized fridge in that project. Okay, so just like you have an overhead tank with its ozonized water being sent for drinking, there was hot water going to the wash basin, sorry. And then this became grey water being non-pathogenic but wastewater. And this was first cleared up by filtration aeration because it doesn't require sewage treatment, and then sent in for flushing. And then when it was sent again for flushing, the effluent was not wasted, it was again treated in a root zone system and then used for irrigation. I'm sorry that arrow is not here very clearly, but it was also used for cooling towers for the central air conditioning that was there in that project. And I think part of it was sent for flushing also, but I don't remember too well now. It was many, many years ago. So you have a look that it is possible to reuse this water within the network quite strongly. How do you treat it? So I showed you already something called a root zone system, which I was running ahead of my story. This is what there are two sorts of treatment systems in water. So this would be called electromechanical treatment systems. That is, they are running on some degree of pumps and other mechanical devices. The bulk of sewage treatment, which basically contains pathogens, is accomplished by what one might call aeration. You have to get sufficient air into the mix for the pathogens to be oxidized away and for the water to become cleaner, clean enough so that it can either be considered disinfected or good for other sorts of use. And so this is 2 methods out of 4 that we have illustrated in the way that the most common is activated sludge on the top, where you basically have an agitator and a set of pipes inside a large tank, which bubbles air from outside into the mass. And then before and after, you can have some settling and some, well, all these systems, as you can imagine, basically the sludge comes out. So the sludge is the solid matter that has gone into the sewage, which over a period of time forms reasonably good fertilizer or manure, and it comes out over a period of time. So typically, you will need to clean all these systems after say 6 months or 1 year, depending on the design, such that the sludge can be taken out. It's often made into cakes and then sold, and sometimes it is just they try to dump it in various places. So it's a mixed story here. Then there are natural systems, or nearly natural systems, I should say. The most common natural system that has been evolved in Germany, in Bremen, in fact, is called the decentralized waste treatment systems, or DWATs. And this was invented when they discovered that most traditional electromechanical sewage treatment systems in our cities were not functioning. They found some 96% or something like that not functioning. And the reason for that is simple. India is short of energy and electricity. So it is easiest for politicians to stop doing the aeration in the sewage treatment plant and supply that electricity to the houses instead, because it fetches more votes. So given that fact, you are stuck with this situation where sewage treatment plants, which were electromechanical, were well designed, were in place, maybe even well maintained in some cases, but were not working. And often the reasons they got was, oh, there's no electricity coming at this point, even though some of the other lights were working and so on. Then there could be, oh, this was working till today morning, but it's not working right now because something's gone wrong with it. So they figured that, this is the real reason that it's not working, is that we need to have a non-electrical system. And this is exactly what was designed by them. So here the job of aeration is done by rhizomous roots of these plants. So essentially, after the same kind of primary treatment of settling and sieving the water to take away the big pieces, you basically push this water by gravity into a sand soil filter, where in the root zone itself, that's why it's called the root zone system. In the root zone, the roots grow rhizomes which aerate this mass, this sewage, and typically it's held for 30 days in this area. And you see in real root zone systems, the dirty side, the plants are actually taller because they have more nutrients to suck up. And as the water gets cleaner and cleaner, the plants become smaller. So that's an interesting thing about the root zone systems, that actually by the time you reach the other end of the gravel and sand bed, you get fairly clean water. In extreme cases in Scandinavia, this system has been used to even treat water to a level where it's been put back to pure drinking water. But in India, we have a ritual distaste for using recycled water for drinking, but we might still be able to think about it for washing and so on. So these are things that you have to see, the cultural biases that exist. And the primary, secondary, tertiary. So the secondary is the part there the biological treatment, the aeration happens. Tertiary is the part which disinfects the water. Now, disinfection can be done in a number of ways. Disinfection could be done by ozonization or by sunlight, which is ultraviolet. And basically, this water that's coming out of the root zone contains only one pathogen, but it's a very important pathogen that needs to be got rid of. It's E. coli, Escherichia coli, which is a bacterium which infests the gut. So it causes dysentery and diarrhea, and therefore cannot be allowed to remain in drinking water. Not even one. When you say 0B, you need to get every bacterium out of that water. So that can be done by disinfection with ultraviolet or disinfection by ozone. Both of them are strong. Ultraviolet, what it does is it disinfects by scrambling up the DNA of the microbe, and what ozonization does is it strongly oxidizes the microbe, thereby killing it. So then you get a storage of this wastewater. And if you notice, this whole thing depends upon this pipe has to be higher than this pipe, because the whole system works on gravity and gravity alone. So when it works on gravity, you have to keep ensuring that you get lower and lower levels in your land, such that you can store your water and then later on reuse it. Now, ultraviolet rays can be also got in the storage itself by putting it under the sun, because sun is a strong source of ultraviolet light. And one has to experiment with how many days it has to stay in that pond under the sunlight. And of course, as you can imagine, these things reduce their effectiveness when it's a cloudy period in the year and so on. So a lot of dewatch systems, they start slightly smelling when it is monsoon. Now, the other system that I've illustrated on this is called the living machine, which is a series of vats which has been created in Cape Cod in USA, basically by a microbiologist. And you get a series of vats in which you get varying degrees of microorganisms. So there's more mollusks and frogs and newts and all kinds of plants that grow in various tanks, and one after the other they are cycled into one to the other, and at the end you can get pure drinking water as well. You will of course need to disinfect it like the DWAT systems. The third one I have mentioned but not illustrated here is the DWAT system. By the way, this picture is one of the polishing ponds, as it is called, or the disinfection pond. You can also think it's a treatment storage tank in Auroville, which uses a lot of DWAT systems. Now, SBT is a slightly different system, and it's been invented by IIT Bombay. It's called Soil Biotechnology in full form. And it basically uses stones as a way of creating the culture required for oxidation. It also uses plants, but it uses a little bit of pumping. So in some ways, a lot of engineers like it because it has something, it's a bit like this, but what it does is it pumps this back again and again and again into this mass. So it reduces the area and it increases the effectiveness by using pumping instead. Now, this is regarding the recycling, but what about usage for irrigation? Now, that itself can be dramatically reduced because this is the common way of irrigation, sprinkler system, which requires a lot of irrigation, as you might be aware. We measure irrigation in terms of per day of equivalent rain, which means that each per square meter represents 1 liter per square meter. And if you say sprinkler systems typically provide 5-6 per day, subsoil irrigation actually can use 0, meaning you clear up the grey water and just pump it into pipes or push it by gravity into pipes in a way that you just moisten the subsoil. So this has been exposed right now in this photograph, but over this soil will cover it. So the soil will simply get wet. Now that can also be accomplished in a similar way by drip irrigation, which does consume some water, but very minuscule amounts compared to that. So it can take as little as 0.5 mm per square meter or 0.5 mm of rain equivalent, half a liter per square meter. And what it does is it supplies droplets of water to the root of the plant and not to the whole area. And of course, this is useless for grasses. And for grasses, we will end up using sprinkler systems or subsoil irrigation, but it's very useful for herbs and individual plants. You can also go in for Xeriscaping your site. In fact, this is a technique I use quite often. Xeriscaping is nothing but simply designing something that doesn't require any irrigation at all or almost no irrigation at all. And succulents, cacti, etc., those that live in desert lands can be called xeriscaping plants. This can also create good landscape, but as you can see, these are thorny and difficult landscapes because that's the nature of these plants when they get so little water. This is also a better xeriscape landscape with a lot of bulrushes and other plants that can survive in extremely low temperature, low water situations, low water regimes. I wanted to end with two case studies. One is Agilent Manesar. I will just give you this thing. This is a method of computing what you can do with rainfall. So typically the method is that you set up July to June, because July is the month in which you can say for sure that you have excess water availability because it's a monsoon month. So you put down here the of rainfall that you expect on an average. You can get this from Wikipedia or from various other weather files on the internet. And then you see how much you can catch. So here is the rainfall analysis on top, which says that, okay, so this is from the sky garden. This is the amount we have caught, 40%. This is from the hard roofs, 80%. This is from the soft podia, and so on and so forth. Hard podia and so on. So in a project, you had so many square meters and so much runoff. And of course, not utilized, one should try to be as little as possible, but sometimes it's not possible to have 0 square meters as not utilized. But so here you get a rough estimation of what kind of contribution can be given by these methods. So for example, in this particular project, you see that 40% is contributed by the hard areas on ground. That means you have to really ensure that these are kept clean. And this was a particular project in which we even made sure that these were cleaned once a day by the workmen who were manning this office space, because this water would be useful to be collected and it's the biggest source, and so on and so forth. Now, when you do this, you can see here that you catch so many out of this, that is the percentage of runoff. It's the average percentage, 46% runoff average. And then this translates to so many liters. And from the bore, you can get so many liters. Now, this is a broad assumption. Ideally, this should be 0 or should be equivalent. If it's 20 million liters per year, then that much must be pumped back in. And then you store this much. So these are a set of simple numbers which you can, I'm sure, derive. So definitely the engineers amongst you will be able to derive this. And then your demand is pretty much constant throughout the year. You see, so you have to imagine that it's a stock in which so much is added and so much more is added in such and such month. And so you need so much to be stored. And then once you need that much to be stored, you have to ensure that this last amount, which is typically in late May, doesn't become negative. So this gives you the maximum storage volume that you require. In this case, it is 5 million liters, 4.788 million liters. And the largest number of this is the amount you need to store, because that's when you will get so much on that month, September, and later on you will get a reduction. And this has to tie up with next month's plus and minuses to reach so much. So you get various ways of storing this rainwater. Now look what this does to the simple calculation of this particular office project, which had 1,800 people using the space. Normally, you would utilize for 1,800 people at least 250 kiloliters per day, 250,000 liters per day, which translates to whatever, something like 80 liters per capita per day, which includes irrigation, which is beyond the 45 or 50 that National Building Code says is required for washing and flushing. So here we identified 4 types of uses: washing, flushing, mechanical, which mainly consisted of 2 kinds, STPs, air conditioning cooling towers, because we used cooling towers in this project because they are much more energy efficient than air cooled compressors, 40-50% more efficient. And then there is irrigation. Mechanical is one more thing. It's car washing in this case, because a lot of people would use cars, come in from Gurgaon. This is a project in Manesar, and they would then have drivers wash the cars over the period of the day. So we wanted to cater for that because that was a real demand. And irrigation. So various qualities of water have been identified here, and these are the various uses. Of course, there's also a small amount of drinking. Now, traditionally, we supply white water. These are the 4 qualities of water: rainwater, white water, grey water, and black water. I should say recycled grey water and recycled black water. So here, traditionally, we supply all 4 in the same quality. So you see the bars, they total up to 250. So all for washing, flushing, mechanical, and irrigation uses, you always get the same quality, that is white water supplied, that is drinking water quality, and therefore the total becomes 250. Now this is what we did in this particular case. We did kind of musical chairs with water, and we said, okay, white water we'll only use for washing. And then we'll blend it for a little bit of flushing because we were short for flushing. And the rainwater we will mainly use for mechanical uses. That is to say, all the cooling towers and all the car washing. We would supply rainwater for that. We'd collect 100% of the rainwater in the 5 million liter tank that you saw earlier in the calculation, which meant a huge basement. You'll see a little bit of rainwater also for use in certain months, extreme months, as white water. So then once you use that much white water, you had it available for recycling, and then it could be used for flushing by recycling. And furthermore, after flushing, it could be treated and used for irrigation. So basically, you jump from this merry-go-round, from this musical chair to that chair to that chair, and you don't require so much white water anymore. So the grand total water that you require at this quality came down to 60 kiloliters per day. So this is how, now this is not zero. Ideally, this should be net zero. So I'll also give you an example later just now of how we created a net zero regime. This was some quick views of this building that had 1,800 people, and which instead of 250 kiloliters, we are using 60 kiloliters a day for the last 15-20 years. These are some real photographs of that building, and I think this one I'm particularly fond of because in the foreground of this building you see the irrigation use that recycled or treated black water has been put to. It is used to grow these salad vegetables, which is incidentally served as salads to the 1,800 people in the cafeteria, which is on the roof. Not here, not this roof, but on the side. And so, in a sense, they are eating their own shit, but of course they are not really eating their own shit. It's been tested and treated for being the right quality before being used for irrigation. But it is part of the cycle of water in this particular project. This is an overall view of the project. The second case I want to cover is IIT Jodhpur, which is in a sense more complicated but very similar, and it's very similar to the earlier diagram that I showed you, where rainwater is a major feed, and we computed that it falls on various areas in different ways and finally either goes into the sky or into the subsoil aquifer. This was a black area, which meant that we could not use it to tap groundwater. So CPCB has identified that this is so water short and it's a desert-like area that we cannot use any water pumped out of the ground. So our strategy then was to, over the decades, maybe 20, 30 years, keep on harvesting every drop of rain into the ground so that it would start growing plants. Now, one of the strategies for this campus was to grow food which was going to be eaten by the students. This is IIT Jodhpur campus, so there were going to be some 12 to 15,000 students at the peak, which is what we are designing for. So we have greens which come water with holding capacity, and then so these come from roof gardens as well as from agricultural gardens, and the rainwater is fed to so many sources, 1, 2, 3, 4, 5 sources, and finally finds its way into the ground. Now, this is the external input that we had. We had a Rajasthan canal feed, which would feed so much per year. Oh, I can't read it just now. Okay, I'll just go to the next slide, which is a detail of the same. Yeah, so up to 550 megaliters per year, million liters per year. So this could be used from the Rajasthan canal, which is quite far away, actually 20, 25 kilometers away. So there was a feeder specially created for IIT Jodhpur. But our aim was to try and make this almost zero. So even though you could establish the campus, we wanted to, over a period of time, reduce the use of this to near zero. And that was the whole purpose of this entire rigmarole that we went through, in which we created a whole system of how much irrigation, how much Xeriscaping, how much we could collect from the even the solar collectors, because solar collectors also have glass and then it's easy to harvest. And there was also drip irrigation used, and we also used dew harvesting. Dew harvesting is an interesting technique used often in deserts, where early morning you can catch the, especially when there are plants, you can catch the dew that falls, which evaporates from the there's a transfer evaporation from the ground, and that can be caught in little nets which capture the dew and can, it becomes practically distilled water which you can use. This was the water cycle. You can see the rainfall harvesting on various buildings, and it had various bases for recharging. It went into air conditioning also, and basically it went into domestic use. All these domestic uses are there. Then from this it went into a simple kind of recycling plant, which was not a sewage recycling plant, but it recycled grey water, which would be used to create flushing quality water. And then flushing quality water would be recycled with a DWAT system or decentralized biological sewage treatment, and then used for irrigation and agriculture, and also cooling towers, which I don't know whether it's illustrated here or not, but whatever it is. So that was the idea. This is how the campus looks, and you can see from the grasses, this was a desert, completely desertified area some 5, 6 years ago, and it has a little bit of water. I mean, the grass is not super green and lush, but at least it's there, which is a big thing. One of the primary elements of this campus was that we created large earth berms out of the soil available and planted that over to reduce the amount of dust that would settle. So we planted, we depended a lot on the greenery to create reduced sand. This was the DWAT system, or what I showed you earlier. This is how it looks in reality. This is a complex little system which you can see a little bit of the sewage water coming on the surface, I think, in this picture, which happens sometimes when there are a lot of students using the shit pot. But most of the time it stays under the surface. And this particular one is designed so that water, the sewage goes inside to the far end and returns this way. This is, see, dewatch systems are very are very space intensive. That's really the only thing that they require. They don't require energy, but they require huge amount of space. They require as large as 2 square meters per person. So considering that we have 10 square meters per person as a working rough approximation for offices and homes and so on, you can see that 2 square meters is a very large proportion of that space. So that's its primary problem, that it requires campus-like spaces. The effluent from this DWAT system goes towards making swales. Swales are nothing but natural waterways. In this case, they were created. You can see here the kind of soil that there existed 5 years ago. And what the swale does is it creates obstructions in the path of water flowing down, and therefore water goes into the soil. And once water goes into the soil moisture and texture improves and plants can grow. So here are some plants that are beginning to grow in the swale, and now it's much greener than it was when this picture was taken 4 or 5 years ago. A little bit of quantification, I think, is in order to end. So here is a calculation for my own house of how we did the total supplies of water, storage of water, and the demand of water. So this is the same kind of calculation that I've shown earlier. I'm sorry. Where you see the basically I put down the days in the month actually accurately, so that the amount of usage is slightly varying according to the number of days in the month. So you see how in the month of September, there's a little bit less than in the month of August, which has 31 days and 30 days, and so on. And February, I think, would be the least of all. Yep, that's right. So that's one thing. So this is the primary water use in our house. This is the cooling requirement. So that was 0 for so many months. And then, of course, in the month of March, April, May, June, you would have some cooling requirement. And this is based on some assumptions and some guesswork, frankly. And then there is the gardening requirement, the gardening grey water availability, because all this that is stored and used as primary, 80% of that is available again as grey water. So I assumed that, okay, in this case, I think I assumed 50% only. So out of 29,760, I've assumed 50% is available as gardening grey, equivalent of irrigation of 1.3 mm. So this is what I do. I say that when we have a garden to irrigate, I tell my landscape architects, and they hate me for it, that instead of giving you 5-6 liters per 5-6 millimeters of rain per day, I'll give you the equivalent irrigation of 1 mm or even less per day. And in one case, I found a landscape architect even telling me, oh, you don't have to give me anything. You give me whatever you have available to you as grey water recycled, and I will design the landscape according to the amount of water that you have available. So that is the way it works, ideally. So this was my final check, that obviously in the months of February and March and April, as it becomes hotter, I need more. So I put up more water. I used more white water as demanded. And then to get all this, I need to store something like 1 lakh liters, which is the size of water tank I have to collect the rain. See, you can actually collect most of the rain that falls, 80% definitely, in a large water tank. But you don't necessarily want to do that because you want to optimize the size. Water tanks can be expensive. I mean, they can take 10 rupees a liter to make. So that is the idea, that you want to optimize the size of the storage so that even when you, of course, if you do it daily, then it will be a different level. You will require a little more. If you do it monthly, like I have done, then you can require a little less, because this assumes that this total storage requirement is after the end of the month. And obviously, during the month, a little more would be required. So, finally, instead of 102,000, we chose a bad year and decided to make an 80-90,000 liter storage in our house while building it. And it's always full, because as this shows you, that's the amount of rain that is there. This is the amount of rain that's caught. In 2 good months, you get 82,000. And so you are never going to undersize it. You will always, I mean, you're never going to oversize it, you'll always undersize it. So here are some other areas and calculations on the same sheet in various ways. And this is the last calculation that I'd like you to visit with me in the form of, in the form of an Excel sheet, which I'll just open and take you through that. So just a minute. Let me just escape from here, close this, and open the worksheet. Just a second. So here I am. Okay. So here's the same worksheet now in a more live form. And this is to demonstrate what we did in order to reach this point. So we had a project in which there was so much square meter of area, 2.5 was the FAR, I think. It is 30 acres. So this is unfortunate, because with so much area which is given to IT parks, it simply means there are many people working. So there are nearly 30,000 people working. And since they would work in shifts, we figured that we would require to have water for 52,500 people or thereabouts per day. Now, how much water? So this, we said 4 liters they'll drink as coffee, tea or water. 8 liters would be washing, with no floor washing allowed, only sweeping, and vacuum cleaners. And then extreme low quantity of 4 2-liter cisterns for flushing. So we figured we could manage with 15 liters, 8 liters and 4 liters, which totals to some 25 liters or thereabout, right? 27 liters per day instead of 45 liters per day, which is the normal National Building Code standard. This translates, when multiplied by 52,481, to so many kiloliters per day, so many kiloliters per day, and so many kiloliters per day. This drinking water, we figured we would have to buy. So we bought this as bottled water, and this is what we assumed. And this 419, we figured we could not use recycled STP water for washing. So we would use borewell water for this 419.9 kiloliters per day. And then this became a resource for us. This plus this would go into the piss pots and the shit pots and become available to flush, as well as become recyclable. So when we looked at, this was the way that we looked at it. So here is our 210 kiloliters of drinking water, which we bought. Yeah. And then this went in, and this goes into the STP, because it becomes sewage, because in this we were not really thinking of separately. You could in theory say that we could have separate urinals, separate WCs, but because urinals are not pathogenic, but we didn't want to go that far. So we said, okay, the drinking water will all go into STP, and from the STP we got this returned, and I think we assumed 90% of 90%. Yeah, 90% of 90% is what we could get. 90% because you can't really collect every little bit of flushing water, and 90% because that's the efficiency of the STP, the recycled output. So 81% we got. And so every time we would balance this, we would have to use different strategies to get this worksheet to balance. This is something that I recommend to the organizers to be given to you as a worksheet, as well as, of course, this whole seminar will be given to you in the form of a recording. So you can have a look. And basically, it meant that from the ground we took 187, and from STP we actually this went to the ground because we said we will recharge 234 kiloliters per day STP water, which is extra, because even when we took the fire makeup water, horticulture water, HVAC water, and flushing water, which we had to play with on those upper parts to get these right, then we still were left with 234 kiloliters per day extra, which we would recharge into the ground. Therefore, we could then draw 187 plus 234, that is 420 kiloliters per day for our washing, which is what we wanted. So you can see that these figures are not fudged that way, but they are backward calculated and forward calculated so that they balance out. And that is the whole game of how you manage your worksheet and how you go back and forth, because you do one trial, you don't get a balance, then you go back and so on. And we figured that we wanted to give 1 millimeters per day because the client did not want a Xeriscape type of landscape. So we said with 1 millimeters per day and then more in the monsoon, you can manage a somewhat herbaceous garden, so that's fine. But no lawns, of course, very few lawns, maybe 10% lawns and so on. So, so this is how we balanced it. We said, okay, so much comes from STP, so much comes from STP, so much comes from STP, so much comes from STP. And the flushing is the only thing that can be recycled. And so it creates, flushing and drinking and washing are the three parts that can be recycled. So this creates 1148. In reverse terms, it completes 1148, comes back here. And so much gets used in these four uses. And therefore 234 is left extra to be recharged. And then we draw 187, and this 187 has to be less than 234, right? That's the key point. So the maximum draw possible has to be the total amount of the recharge water plus the rainwater. See, 187 was the amount of rain that fell. Here it is. Rain recharge, which was, we tried to make it 100% as much as possible, 90% runoff recharge. Rain recharge, even at 650 mm, was turning out to be 187. So we could draw 187 from the ground, and 234 agreed that we would be drawing in dry seasons more water than fell as rain for that day, but we would be drawing much less in the monsoon where it would be getting recharged. So this is how we balanced it to a near zero or a zero water regime. But it still meant, in this case, because of the 50,000 people that we had to cater to, that we still had to get 210 kiloliters per day, which is a very large amount. Huh? It's like 50-60 trucks of water, 70 trucks of water from outside. So we had to buy it. So we actually started, because this is a very large SEZ project, we started working out a train of trucks to be brought from the Yamuna, the Ganga Canal, from near Meerut, where we found a source of water that is available. But this project didn't come about, so we don't know whether it would have worked or not. However, this was to just give you a flavor of how this whole business of net zero goes when you actually get your hands dirty and start working out the computations. So thank you, and I'm open to questions. And Yashima, if you could just moderate the questions for me, it would be very nice.
Sure. Thank you, Sanjay, for the presentation. And we have had some questions coming in, and we'll take them
I'm
now.
afraid I've taken more time than I planned to, but that is usual.
Yeah,
I'm
that's
willing
not a
to come on a
problem.
little longer also, even though the proposal was only for 5:15, which is almost is now.
Yeah, sure. Yep, thank you. Okay, so the first question that we have is how to take into account permeable concrete used in hardscapes in water budget equation.
Well, permeable concrete, you'll have to find out from the manufacturers what the permeability is. There's another little trick that I did not mention. I often take out 5 of rainfall every month from the water balance calculations, not because it's going to be a drought year, but because I figured that when we have water falling, when we have surfaces receiving rain, the first little bits of rain and little bits of rain that fall sporadically don't get runned off. They don't run off. They just get absorbed in the surfaces on which they fall. So there's no runoff really. And so to be a little conservative, I take about 5 of rainfall every month. There's no real science behind this. It's just a judgment. And frankly, even this business of how much permeable concrete would be able to recharge the ground is a question of faith in whether the manufacturer is giving you an honest opinion or a calibrated test report or is just marketing spiel.
Right. Next question. Does the DWAT system work in an extremely cold climate?
Yes, in fact, the DWAT system works in northern Germany quite well. Though in extreme cold climates like in Sweden, I believe they put in some solar heated water or other kind of heated water to make it work. By the way, the living machine system doesn't work in cold climates at all because it depends upon mollusks and living creatures to create the savings, to create the aeration, and therefore it stops working when there is no plant growth or animal culture possible. But yeah, DWATS generally works because the plants are fairly hardy. Cannas is the most common plant used by DWATS. Um, and its only problem is not even the maintenance or the heat or cold, so much as there are two problems that I can identify are that it starts getting a little bit oversaturated, so it requires a good gardener to tend to it in the monsoon. And second is it requires a lot more space than regular electromechanical systems. Electromechanical systems typically occupy some 100 square meters and they can handle very large volumes, but DWAT systems require 2 square meters per person.
Right. Thank you. Next question. Is there any thumb rule in sizing the root zone treatment tank?
Yeah, 2 square meters per person is the thumb rule for residential complexes. Obviously, less, zero point 0.8 or something for offices, and that's really the thumb rule. This is the plant bed filter part, and of course, there are some attachments to that would add to this area. So it requires a substantial amount of area. Sure.
Right. Next question. How to design rainwater harvesting tank in a sustainable way?
Well, what I did was that I chose not to build it in concrete because concrete uses a lot of cement and steel, which are high embodied energy materials. So I also had to make it inclined. It's not a mud tank, but it is a lake is in a sense the best way to actually design it, except that you would lose more than a meter of height of water in the hot summer that we have in most of North India, if that's where you're designing. But a lake with something covering it to prevent the evaporation would be an ideal solution because a natural or an artificially made lake with bentonite or clay lining is obviously quite a sustainable way of making a water storage tank.
Thank you.
I don't know how to
Next,
make it though.
sorry.
I wouldn't know how to make it. Actually make it store water.
Okay, so the next question, what are the aspects of residential buildings that use up a lot of water which need to be taken care of while planning our approach?
So the biggest single use of water in residential buildings is flushing. The second largest is bathing, because these are the two primary uses. And in fact, of 135 liters, you could say that 80 liters is taken up by these two functions, 50 plus 30. And another very big use, but it varies very dramatically, is that if you have a large garden, and especially if you have a lawn, you could end up spending 5 liters every square meter every day, just keeping that lawn in shape. It depends. If you have exotic grasses, you would have even more required. But if you even have local grasses, you would require quite a lot of water. So generally, lawns are considered the least green part of the greenery.
Right. Next question, how is sludge handled at the end of water treatment?
The sludge comes out, if you go back to those diagrams, the sludge will come out in a variety of ways at the bottom of these tanks, and typically it's let out in flat beds to dry, so that whatever remaining sewage is there evaporates and only the solid mass remains. And then typically it is either cut up or mm, taken as a slurry into tanks, into large trucks, and then disposed of. When I say disposed of, the best disposal, of course, is to be put on a soil, because you must also realize that one of the biggest things that modern society does is it separates us from our farmland. Traditional societies used to keep us close to our farm, which meant that the night soil that we created, which was nutrients, would return to the soil directly or indirectly, either through animals or directly as night soil onto the field. But in today's system, as soon as we have a sewage, WC, for example, it means that we create sewage which belongs to the fields, but which is then going back to the field. You realize that this is the primary reason why we have floods and droughts. I mean, we have, uh, in the monsoon, we see that so many parts of our country have a lot of erosion, and so many parts of our country have floods. The reason for that is that by ensuring that we take away nutrients from the soil and not returning it to those fields, we actually screw up the whole nutrient balance of our soils. And the soils no longer can have the kind of soil moisture required to not erode. So they will erode in rain. That's one part. The second thing is that, on the other hand, cities put out a lot of their sewage, often untreated, into the rivers. And this causes a lot of siltation and a lot of flooding as well. So these are the two reasons that modern society has seemingly invented, which are not necessarily the best way to go. But this is one of the reasons why a good net zero water regime would also help to solve some of these side problems.
Right. Moving to the next question. Can you give more information about dew harvesting, as in which nets to be used, or at what location can we establish dew harvesting? Are there any calculations as to how much water can be generated from dew harvesting?
Not much, I believe. But if you go to the internet, you will find that dew harvesting has been recently used in Malawi and places in Africa to actually supply reasonably large quantities of drinking water to entire villages. But that they've been done in large acres, and some kind of fishing nets, etc., have been used. Not fishing nets, which are much smaller nets, of course, are required for dew harvesting. And frankly, I don't know the calculations, and I suspect it doesn't work in extremely dry climates. So it works only in climates which are somewhat not that dry, even though they may not have vegetation.
Right. Another question about the DWAT system. So, what area is required for DWATs in terms of wastewater produced in liters per day?
The same amount that you would put in, right? So, for example, uh, the way to calculate a DWATs area is as follows. You take the total quantity of sewage you are putting in, which you can compute from your water consumption calculations, and you hold it for a depth of say 20 centimeters or 30 centimeters over 30 days. So that's the area you require. You can divide the whole volume by zero point 0.2 meters or 0.3 meters and get an area that you require for the plant bed filter, because that has to be held for about 30 days to make it reasonably clear. And well, I don't know. I hope that answers your question that you were asking.
Right. Next question. How is it feasible to give water pond at the end of a root zone system in a residential project?
That I have to leave to you. It's often, if you don't have space, you can't easily give it. You will have to then depend upon more energy intensive methods like AquaGuard, for example, is an ultraviolet radiation machine, or ozonization, which is relatively cheaper for large volumes and is not very energy intensive, but takes up some energy to produce from air. It produces ozone and bubbles it into the water, and so on. So, disinfection, you will agree, is necessary for producing drinking water, but how you do it through a pond or any other way is finally up to you.
Thank you. Next question. What is the cost of a DWAT system than the normal water treatment? Is it more or less?
It's the cost of the civil work. You see, after that, I mean, so you will, if all of you will have some civil engineers in your team or architects in your team, they need to investigate what's the cost of deploying that much land, making waterproof channels of the kind I showed you in the photograph, and putting gravel and sand into it, bought if it's not locally available, and then planting the seeds and watching them grow. And then, of course, the cost of maybe one or two people in operations to look after them, to watch them grow, and to look after them when they don't grow well, so that
Hmm.
they're either replanted or they are transplanted, etc.
Right. Next question. How do you manage transpiration loss in swales in desert climates? Can you explain showing your example from IIT Jodhpur?
Yeah, actually, you don't. If you look up, you will find in YouTube a lot of examples of swales. And what they do basically is they send the water down very quickly. There's no sun there to make it evaporate. It basically is a method to improve soil moisture. It's not as if it's there is some transpiration loss, of course there is, because the plants that are growing using that soil moisture will evapotranspirate, but it's not very huge. I mean, if open ponds reduce in height by about 1 meter every summer in the desert, it's a quick guess that this would evaporate about 1/5 that amount or 1/2 that amount at most. So a lot less is lost in evapotranspiration. I leave you to find out how much is, because frankly I don't know, never thought about it. But the main thing is that swales primarily send the water that is running off somewhere into the ground. In this case, all the excess STP water in IIT Jodhpur has been sent into the ground.
Thank you. Next question. Can we treat and utilize water from saline water content in air near near to coasts for SAR treatments of any type?
Yes. Desalination of water, however, is an expensive technique. And since the solar decathlon expects you to get approximate estimates and make it affordable, not only the capital cost, but also the running cost has to be affordable. Desalination is done by many desert countries, especially in the Middle East, because they have lots of money. But it's not something that I would recommend to use en masse in an Indian kind of situation, because you will not going to easily get desalinated water. I don't know where your saline water is coming from. Is it from the sea? If it is from the sea, then yes, you will find various nations, for example, the Sultanate of Oman, UAE, and Qatar, use water from the sea and desalinate it at a mass scale and use it for drinking and for domestic use. But as you can imagine, this requires a huge amount of oil and oil money to be able to make it feasible.
Right. Thank you. So we also had another question in the chat window, which I'm going to take up now. The question was, can tapping collected groundwater be counted as a part of water trade-off in a net zero water building?
I would like to answer yes. Can tapping, yeah, I mean, if you recharge ground with that quantity, then you could count it as, like I did in the last example of the IT-SEZ, which I showed you. Then I could consider that as equivalent of water available to me over the year. Exactly how you would do it, of course, is up to a lot of detailing to work out, because there are monthly issues, there are trans-evaporation issues, and so on. But on the whole, I would say yes. I would accept it if I were a juror. I would accept it as a valid way of trying to reach net zero by basically recharging the ground with not just with the rain, but with STP treated water, and then only using that much to draw from the ground. So even though it is fossil water that you're drawing, especially if you do it from the shallow aquifer, it's not that bad.
Yashima, Amanda
Yes.
probably would like to add something here. So I think the way we are looking at net zero water and its definition for solar decathlon is kind of what Sanjay has said. The clarity here is that if you are using groundwater, then you need to treat it to be and return the same quantity with a similar quality back to the ground. Amanda, do you want to add anything there?
Nothing, Prasad. Yeah, so the quality is important here in terms of, it should be, it's important that it is treated before it's recharged, left for recharge. Yeah.
This brings me to an interesting story from Germany. You might be aware that in Germany, people pay as much for their water as they pay for their electricity and gas for heating. And the reason for that is that they made a very simple law in Germany, which required Germans to pay for water which was wasted at the same rate as the water. I mean, they are now paying for water to change the quality of the wastewater to the same quality as the water they are supplied. So whatever it costs them, the municipalities are supposed to charge that much. Naturally, you can see it's a very large charge, and therefore, especially the drinking water quality in Germany is very good. So the municipalities, whether they do it or not, they simply charge the same amount as if the sewage and wastewater coming out of the houses were to be treated to the same quality as drinking water.
Right. Next question. What are the plants used for aeration in DWATS and SBT system?
The most common ones are called cannas. These are plants which have rhizomous roots which can aerate at the root level. But I leave you to do your own research and find out what else there are. There are quite a large number of plants, I believe, which can do this.
Right. Next question. If we have sewage treatment plant at little higher level on site, is there any other technique to collect it in STP rather than the pumping technique?
I can't imagine anything. You can, please enlighten me. I don't see how water can flow from a lower level to an upper level. And basically, sewage is water, more or less. 99.9% is water, only 0.1% is sludge. So,
Right. Okay. Next question. Yeah, let's take this one up. What should be the water management system when there is too much rainfall annually and the groundwater table is high, but we cannot dispose the water off-site to accomplish net zero characteristics?
this is an unusual case because you're saying that you actually have too much water.
Yeah.
Well. I don't know. You will have to find some ways of doing something interesting with it, including evaporating it. If it's got so much water, it's likely to be a very humid climate, so not much will evaporate also. So I have really no answer to this one.
Yeah. Okay. I think following that, we had this other question. So if we choose to store, so won't storage also be a big issue? Like how much space would a 1 lakh liter would 1 lakh liter water storage tank take up?
My 1 lakh liter storage tank in the backyard takes up a space of 6 meters by 6 meters by 5 meters deep. That's more than 100 cubic meters, but if you multiply these three numbers, but the rest is taken up by the lining on the walls and so on and so forth. And its roof, which is the important component, is supported with piers of bricks every 2 meters, so that I could create the roof out of stone and not concrete. So there was an earlier question of how do you make a sustainable water storage. So this is part of the answer, that you have to try and reduce the amount of cement and steel. And one way to do it is to reduce the span of the roof. You are unfortunately forced into some kind of a roof to prevent evaporation, unless you have so much water, as one of you had given in that question, that you can afford to store and allow it to evaporate.
Right. Next question. So recycling water twice or thrice can recycling water twice or thrice make a net zero water building, or is it compulsory to use rainwater and then recycle and reuse it?
You could use recycled water, but let me say one thing: if you don't have an outside source, no, you won't get closure, because every pass of your recycling you lose some water. You can't collect 100%. You can't recycle 100%. Little bits will evaporate, and then you'll find that you are short in the next cycle when you can compute. So simply recycling without any additional input from outside, like from rain, is not going to work, in my opinion. But if you can make it work, well, good luck to you. There is one little point that I forgot to mention while I was going through this. Of late, I find that most sanitary engineers prefer not to recycle twice, but they prefer to add the gray and the black water together and treat it once and then supply it back to only flushing. So if that system works for you, then that's good luck. I think that will be fine. Then you'll still need rainwater to supply the washing water and the drinking water. So if I were to make a quick breakup, saying drinking, washing, flushing, and irrigation as the four main types of waters, then you will still need washing and drinking with white water, which might mean either rain or some other kind of source.
Right. We have another question. So can we combine storage tank of recycled water and collected rainwater?
Normally not, because you'll find that recycled water is not the same quality as rainwater. Rainwater is practically distilled water, except that it has picked up a little bit of impurities when it runs off surfaces. So it has some dust and it has sometimes calcium and various dissolved solids. but it is pretty good. And therefore, recycled water is often used, rainwater is often used for mechanical uses. In my own house, I use rainwater for the washing machine because in clothes washing, it improves the life of the washing machine quite a lot. It's very good quality water. And on the other hand, recycled water, besides the cultural difficulty of understanding that it's recycled, there are simply purity differences between that water and collected rainwater. So I would not really want to store it in the same tank. But yeah, it's quite easy to do a partition in a tank and create two different chambers for storing different qualities of water. You just have to be careful that they don't contaminate each other, and that's the main thing.
Right. Another question, can we use recycled grey water for fire water storage?
Yes, it was not allowed earlier, but fire water storage doesn't take up too much water, as you will notice from my IT-SEZ calculations. What happens is that even if white water, municipal water in this case, comes in, typically fire water storage is a one-time storage. Okay, when a fire happens, that is when it gets used. But on a daily basis, you only need to make up whatever evaporates from it, whatever it loses. So that is much less, and you will see from our IT-SEZ calculation that despite the other numbers being very large, the fire makeup is a very small quantity. So fire doesn't have to be a big issue, because what happens is that you store a lot, and the overflow of that then goes into the rest of the uses. That's typical of all fire tanks and the way they are. But surely you could use recycled water there. You'll have to find out what the TDS, the BOD and COD of the recycled water is before making that decision.
Right. Another question, I think this is following what Prasad said. So if recycled water is used for groundwater recharge, what should be done to improve its quality?
And it should be treated before it's recharged. So you'll have to find out what is an acceptable level of treatment. So in an extreme case, one should make it equivalent of drinking or washing water. But I don't think we would need to go that far. As long as we can get this to be pathogen free and TDS free, I would accept it if I was in the jury to be used for groundwater recharge. Ground itself can filter a lot of TDS and even to some extent the amount of pathogens in the water. So there is that too. Now somebody has asked, water pumps makes a lot of energy being waste. Can we draw water without electrical energy? I don't know how to. You can do it with manual energy, but I believe you can only do it from 30, 40, 60 feet, not more. But animals, manual. I've actually designed a building many years ago in which we used foot pumps to pump water. We used to collect the rain. There was no rain connection there. There was no water connection in that. It was a very wild area. And there was no electricity and no water. So we would harvest the snow and the rain. It was a cold area. And we used to put it in underground tanks, which were all the foundations and the foundations of the buildings that we were designing. So from those foundation tanks, we needed to pump it up on a daily basis for the day's use, right? So I figured that since it was some kind of a resort, that maybe the best option would be to get foot pumps, which were like cycles. So we would then encourage all the guests to spend time in doing a little bit of cycling, and in the bargain, they would, in 5 minutes, they would pump up one day's use of water into the overhead tanks. So yes, so you could do it that way, but I doubt if that kind of thing is the kind of situation which you can manage.
Right. I mean, that's where the innovation lies. I mean, we have a separate category for innovation and
Yes.
yeah. Okay, one last question for today that we will take now is there an efficient sizing of root zone treatment? What is the maximum quantity of water that can be treated by root zone treatment in a day? And how efficient is the root zone treatment in an individual housing level?
So the root zone treatment can manage very large cities. In fact, in the city of Bhuj, the organization Hunar Shala has implemented a very large city-wide root zone system. I saw that, and it is acres and acres of root zone. So, and even the polishing pond is many acres. So it can be done at a very large scale. So that's not the problem. What is the other part of the question?
What is the maximum quantity of water that can be treated by root zone treatment in a day?
I guess there is no limit really. I mean, you
Hmm.
can really send a lot of water into a root zone as long as you hold it for 30 days and aerate it with these roots. How efficient is the root zone system in individual housing level? Well, how efficient or efficacious is up to you to work out. If there is a shortage of space in the individual housing, okay, in individual housing in Auroville, you'll find practically every other house has a DWAT system in operation, partly because Auroville Science Center got a grant and then training in the implementation of DWAT systems. But this comes from an organization centered in Bangalore. Dissemination of DWATs, something. If you Google it, you'll find it. But it is what it means is that I have noticed how in Auroville they actually dig up portions of their individual site in an individual house to reach a lower and lower and lower level so that the polishing pond, because they have very little electricity also, so that the polishing pond can actually sometimes be in a bit of a hollow and you have steps going down to it. It's like a kund almost. So it can be done, but it has these issues.
Right. And while we were discussing, we have this other question. I think we'll take this as the last one for today. Is root zone water system possible at a smaller scale, like for one public building?
Yes, definitely. In Auroville, I just mentioned, they go as small as one single house. That means they have something like 8 square meters of root zone, followed by a polishing pond, which might also be 8-10 square meters, and that's it. And the picture I showed you in the root zone slide, which you can go back to in the recording, contained a lot of duckweed, and that was on a polishing pond. So that was an individual house polishing pond, and so it's really possible for a public building, definitely, even for individual house.
Right. And with that, I think we're done for the session today. Thank you, Sanjay, for your presentation. And I think the Q&A was very helpful too. And I hope our participants can make the best use of the knowledge and practices you have shared today. Thank you everyone for participating today. And we will see you on November 21 now for the next webinar at 6 p.m.